Okay, with that, it's my pleasure to introduce to you Thomas Coleman with Silixa. He's been with Silixa since 2014 and has been involved in activities ranging from field installation, surveys, data analyses, installation and component design, and business development. In his current role, he oversees Silixa's environmental and infrastructure business in North America, including both carbon capture utilization and storage, geothermal, geotechnical, industrial, and defense sectors. Thomas holds a BS in geosciences from the University of Montana, an MA in water resources engineering from the University of Guelph. Did I pronounce that right? That's
Close enough.
So I've learned that Guelph is in Toronto.
Just outside Toronto.
Just outside of Toronto, and it's a focus group on hydrology and fractured rocks, right?
Correct.
And he's currently working towards an MBA at the University of Montana. Thomas has numerous publications related to fiber optic sensing applications and is a co-principal investigator of a Department of Energy funded research program. In 2021, Thomas was awarded the U.S. DOE Secretary's Achievement Award as part of a source physics dry alluvium geology team. That's pretty cool. For contributions to advancing the science of nuclear explosion monitoring. So please welcome Thomas.
Invitation to have me come down and talk to you guys, and thank you, Christine, for all of your organization. I've been extremely impressed at how tight a ship you run here at SCR. So it's been a very pleasurable experience so far, just coming to visit. So yeah, so today I'll be talking about distributed fiber optic sensing, really an emphasis on carbon capture and storage applications, but really it's broadly applicable to a lot of permanent reservoir monitoring techniques. And so I'll talk just a bit at the end about this geothermal project we're involved in. So Silixa, so we're headquartered in the United Kingdom, and that's where all of our fundamental sensory R&D comes from. So at our core, we're really a distributed fiber optic sensor company. But then we become quite vertically integrated and we work a lot on everything from field deployments to data analysis and surveys. And so our core office, our headquarters it's just outside London. And then we have two operational facilities in North America. One in Missoula, Montana that I manage, and then one down in Houston that is focused on the offshore oil and gas sector, and then also working on unconventionals. And then we have a few other clusters of personnel sort of at strategic locations around the world for supporting other activities. And we work now on all continents. We have one project running in Antarctica. Actually, I guess the second one kicked off. Yeah, and we've been involved from the early days. I guess mostly in the oil and gas sector is what the backing for Silixa was, and we've really expanded out to other areas, broadly in the earth sciences and energy transition. So I've got to go to plug. So our Missoula facility, I'm too embarrassed to show a picture of what it looks like now, but we're currently renovating it. So this is sort of what it's going to look like in about a month and a half time. So it's really an operational base. We do a lot of cable terminations. We have a pretty strong geophysical team here and project management, and then a field operations team. So we're growing in Missoula, so not too far away from you guys. And then broadly, Silixa, we do a lot of we work in quite a few industries, but the largest tie for our work is all earth sciences. So, we worked in monitoring hydroelectric dams, for example, but a lot of downhole work, in the energy transition space right now, I think is the area that we're seeing grow the most. And I mentioned we're vertically integrated, so we do everything from design engineering services where we have expertise for, downhole installation, component design, but also, here's a picture in the top left. I mean, these are custom panels to go around reactor vessels at a petrochemical plant, to hold fiber optic cable. So we do a lot of design ourselves, and we have some capability in-house to do CAD manufacturing with CNC machines. So we like to, I think we do a lot of innovation, and we're always looking for ways to install fiber optic cables to monitor some new process. So we're here a lot. Installation, hardware, and services. We have a team based in Missoula and one in Houston that does focuses on downhole installations. So where we well, I'll have some slides later where I show what this looks like, but we're really attaching fiber optic cables to the outside of casing most of the time for permanent installations. And we provide the best in class interrogators. And so interrogators, that's where we're interrogating an optical fiber to tell us the information that it has. And so whether that's we can measure acoustics, which is used for seismic surveys, temperature or strain. So we manufacture, design all our own interrogators. And then we have a pretty robust geophysics team. So we do survey design, but also a lot of in-house analysis and reporting for surveys. But I think the biggest area that we've been working on the last couple of years, and I think it's what, carbon capture and storage is one of the areas driving this, are these integrated monitoring platforms. And that's really where we try and do as much data analysis and reporting sort of in the edge as possible. So we're rather than just collecting data sets and then going back and trying to do post-processing of those data, it's to provide answers, immediately, and where we're trying to minimize the costs for doing this analysis later. And I would say it's probably the largest development project ongoing at Selexa. So we've got some areas that are fairly mature and other applications we're continuing to develop. But that's where I think the future lies for us. So Selexa, we're a distributed fiber optic sensing company. I realize that a lot of folks are probably like, what the heck is that? What is distributed sensing? So it's a light-based measurement system. So we couple pulses from a laser into an optical fiber, and then we're measuring this light that's naturally reflected or backscattered towards the source. And we do this, it's called optical time domain reflectometry. And what that really means is just we know the speed of propagation in a fiber. So if we just measure the time from when we launch a laser pulse, and then we measure the time to when we receive signal, we can calculate the distance along that fiber where that signal came from. And that signal happens to carry a lot of information about some of the physical properties of the fiber. So we can quantify that information to create these sort of vast distributed arrays, so that are equivalent of thousands or really tens of thousands of discrete sensors, just using optical fiber. So here, I think one of the simplest ways to look at distributed sensing is just looking at temperature. So here's just a table that we laid out. This is in our office, and just showing that, we're really measuring continuously in space-time. So this is sort of 24 hours of data in our office, just playing through time. And so we do this with temperature, with strain, and also we can turn each of these points in the optical fiber into a distributed, into a discrete seismometer or acoustic sensor. So there's all kinds of things you can do with these data. Yeah, so that's an example of temperature sensing, and we don't really have to trade off measurement performance when we do these measurements in fiber. So with temperature, for example, the measurement resolutions can be on the order of 1/100 of a degree Celsius, and we can collect data every 12.5 centimeters along the fiber to be a discrete sensing element. And with strain, very fine resolution, and then acoustics, we can measure on standard fiber, and then over the past few years, Selexa has developed this enhanced fiber that it basically gives us more light back towards the source in a very controlled manner that now allows acoustic sensing to match or exceed some of the very best point sensors as far as the actual noise performance of these sensors. And I'll talk a little bit more about that later, why that actually matters in practice for some of the applications that we work on. And here in the middle, it's this graph, that's basically the spectrum of light. So if we send a pulse in to a laser, then we looked at all the light that's coming back, we would get this whole spectrum, and that spectrum of light is what's carrying this information about the point scattering. And some, like the Raman spectrum here, it actually is temperature sensitive, where the amplitude of that light changes as a function of temperature in relation to true absolute zero Kelvin, where it's related to the molecular vibrations actually of the crystalline structure. And then where the Brown scattering is actually a function of the density of the glass, and it sort of it shifts in frequency or wavelength as a function of density. So that's how we measure strain, using that portion of the light. And then the Rayleigh scattering is something that it's an inelastic scattering, elastic scattering mechanism that we can use with some really advanced processing actually to measure acoustics. And So most of us, when you think of fiber optic cables, you think of that something I want to avoid cutting that. That's expensive, that stuff's delicate. And you wouldn't necessarily automatically think that I install fiber optic cable in really harsh downhole conditions, right? But really the reverse is true. It's the optical fibers themselves, it's made of glass, but really you can package these optical fibers in such ways that it's incredibly resilient to high pressures, high temperatures, harsh chemical environments. So yeah, so we direct bury on cable at the surface, but on the far right here, this would be a sort of a classic 1/4 inch downhole construction that would look like a 1/4 inch control line or something from the outside, but really it has optical fibers packaged inside this cable, and we can make these from all kinds of alloys. So for CCUS, like if we're near injector wells, we can use Incolloy alloys that are extremely corrosion resistant, have a long lifespan, and we can make these cables for downhole use rated to 300 degrees Celsius. And so, it's completely passive. So it's the advantage of having all the sensitive electronics up at the surface. You don't have to that stuff doesn't have to survive the harsh conditions. You can actually just have these passive sensing on downhole. And then we design and manufacture a lot of our own, all of our own installation components. So we have to do terminations that handle high pressures downhole, where we can splice fibers together, and there's reasons we can do that where we might want to daisy chain wells together, or we just need to provide a high pressure seal so you don't have fluid migration up the cable is a concern. If you need to pass through a packer or you have a cable break, you have to be able to splice fibers downhole. So we have our own components that we designed to do this. And really, it takes all these parts coming together, I guess, to be able to work in this environment. So I have some photos of looking at installation options and some photos. So we can install cable cemented behind casing. You can install it, pseudo permanent on production or injection tubing, or run temporary interventions using a slick line or wireline type deployment. For permanent monitoring, we most commonly install cable cemented behind casing. And so carbon capture and storage, that's really where the bulk of the installations that we're working on are going. If it's a retrofit or an existing well, we can, it's fairly straightforward to install and just clamp on the production tubing or injection tubing. But then there's considerations with if you need to pull that tubing, you obviously have to worry about the cable and things. That's sort of not just tucked away outside of the casing. So some photos. So this is what an installation looks like. This is actually a geothermal installation here from last year. So yeah, just cable going up over the ship and down to the rig floor. We test continually running in holes. So you want to identify a problem right away. Most of the issues wouldn't tend to occur downhole. A lot of the risk is at the top hole side, just for accidentally bending the cable too sharply or getting crushed somehow, like when the slips or something. So we're always monitoring for those breaks early. And then so we work with specialty protectors and plant components to keep the cable intact. So on the far left here is just an example of a protector around that bottom hole assembly, and then the wrist points are really across the couplings. So there's a lot of different designs, but we're really trying to keep that cable from being pinched across that coupling, and also it's the joint centralizer, so to keep the casing centralized. And on the right, obviously that's a downhole splice going together. So where we pressure test, everything has pressure test for it, so we can actually make sure it's going to survive when we run a hole and not have a nasty surprise. Then once you get to bottom, a lot of the risk then is really at the surface completion side of things and getting that cable through the wellhead. So where we really want to have low angle exit ports in the wellhead to make sure that we don't have to bend these fibers really tightly. And then we work a lot on the wellhead design to also have space for having wraps of fiber before you exit. So if there is an incident, you break the cable, you actually have a mechanism to fix it, rather than just having a 6-inch section of cable that you're kind of stuck with. So a lot goes into the design just to minimize risk there. And then once all is said and done, you end up with a stainless steel box, single box or something, where you have the cable terminated that we could run into some sort of permanent monitoring shack, or for temporary or discrete surveys. Someone could do drive-by surveys to collect data. So now that we have cable in the ground and we can measure things on it, well, like what are we interested application wise in actually measuring? So there's a ton of things in those applications, and applications are continuing to expand. So this is sort of the more common things we might do. And with temperature, looking at cementation evaluation, we can measure, at least I guess the cement height is sometimes a real question, right? Because you're using estimated volumes and using a caliper log to try and figure out have we actually cemented up to the right interval, so we can measure that live, and then in high temperature wells also help guide the thermal inhibitors that are used to make sure the cement doesn't cure too quickly. So you don't have to make assumptions about what that temperature is. You can actually measure it, and we're going to look at monitoring wellbore integrity. So whether it's migration up to cement or some other issues in the wellbore. Reservoir temperature distribution evolution, pretty generic, but in some we've worked on like one CCUS project, for example, in a very karstic environment where you could actually get temperature rivals in the monitoring wells because of such limited surface area and such significant migration of CO2 at distance without thermal decay. And for acoustics, again, you can listen for leaks, listen for problems, and it's often referred to as a noise log. It's a lot more advanced. Like, this is a truly coherent acoustic array, so you can do all kinds of really advanced processing with it, rather than just saying that if there's noise there. Real-time seismic monitoring, microseismic events, seismic imaging. I have a case study, an example of doing time-lapse VST later in the talk. Flow allocation, so both production and injection. You can actually look across different perforated intervals and say where is that production going, or that coming from, or where is that injection going. And for strain, so we're really monitoring the deformation of the cable. And if that cable is coupled like outside the casing, then the hydromechanical response, we can couple then the pressure response to this deformation. So you can sort of fill in the gaps. You might have a downhole gauge, and you can fill in the gaps in between to get how that pressure signal is actually reaching the monitoring. So yeah, and there's a lot of different advanced things you can do there for tomography purposes as well. And then all of these techniques combined, when there's stimulation, you sort of combine to characterize the stimulation where you have fluid going, where the fraction network is growing. So specific to CCUS, and I think there's folks in the audience that know much more than me about this area, but the EPA lists requirements for monitoring, and then CARB has some unique requirements as well. And a lot of them I've just talked about, things we can do with distributed sensing, and really for looking at integrity, pressure development, and then where is the flume going. And typically that's the time-lapse seismic techniques we would suggest. So again, there's some direct measurement used as well. And then CARB requires long-term seismic monitoring, so we can actually autonomously real-time detect microseismic events, and then so we can get a timestamp and the location of the event. You can triangulate the distance away from the well using the different like the PNS wave arrival time, and then estimate the magnitude of the event. And then I think really, all of this is dependent on a really robust baseline characterization. So there's some direct measurements that are really useful just for getting baseline profiles, and that we can collect, but really, I think where a lot of the energy goes is into a really quite robust 3D VSP or 3D seismic survey. And it's something that's a trade-off between obviously the costs and getting coverage, but it's something that you only have one chance to do and get it as good as possible, because from then on you're doing differences versus that baseline VSP. So it's an area we always are encouraging folks to spend the money and maybe make that survey as good as it can be, because later on you'll spend that money maybe in processing costs with trying to tease out small differences that would have been easier if the survey was more robust. So really, this is what our platform looks like, where we collect data with the base interrogators, and we have this edge processing platform. So, and the reason we have to do that is gas data sets are going to be immense. We can sample data at every 1 meter might be common, so every 1 meter spacing in a well, and we can be sampling a couple thousand samples per second. So these data volumes add up into many terabytes quite quickly, and really hundreds of terabytes a year. So you have to be analyzing that data live. You can't store it. So what we do is have a platform where we can if it's microseismic, we're running that detection algorithm, and you're pulling out and extracting the vents, and then you can delete the raw data. Or if it's a time-lapse seismic survey, you you basically, you extract out the shots or sweeps and do the cross correlation waveform or waveform deconvolution, and then you delete the full raw data set that you don't need. So that's something we know with these rotating buffers of data. But really, the system is designed for remote operation, so we do as much remotely as possible, as much processing in the field. So we're just streaming smaller amounts of data offsite for the most part. There are some exceptions for very high-profile projects where they want full bandwidth streaming, and they put in a significant infrastructure to be able to handle that. So ultimately, we look at it as a very cost-effective solution, primarily because you have these permanent arrays. There's no interventions required, and so there's minimal amounts of mobilizations to site, and for some of the operators, I mean, this is quite significant for safety considerations as well, as they really don't want people on site very often. Every time you mobilize, that's a risk of some lost time injury event occurring. So, yeah, what do these systems actually look like? So it completely ranges in scale depending on how much we're trying to do, how many of those applications are we trying to do at once, how many wells are there that we're trying to monitor. So I guess there's a schematic on the left of one system. Here's a system that's sitting in our office right now, getting ready to be installed on a site where we're monitoring 3 wells with the system. So we have some of the wells are all daisy chained together, but we're collecting all these data sets, and there's a lot of hardware here that goes into this syncing timing and doing processing. So it's really scalable, and on the simplest side of things, it could just be one sensor and a couple pieces of hardware that sit in an event closure. So it really just depends on what the requirements are. And then sort of a different view here of how we can leverage monitoring multiple wells with just one set of the core interrogators. Those are the expensive bits for the most part. So you really want to leverage that to monitor as many wells as possible. So if the wells are on the same pad or close together where you can run surface cable linking them together, we'll do that fairly commonly. And then we're on our analysis, it's just basically a really robust server, and we can run these different analysis nodes for different applications to then provide the answer products. An even more complex view, there's a lot of work that goes into data handling and just trying to get these systems to run and provide what you need. So we're at different phases of maturity in different application areas right now. So like microseismic is coming along to be very more mature area, and time-lapse seismic. Yeah, but this is really the feature, I think, for us. So I'll just step into a case study for carbon capture and storage from what I think it's really one of the flagship CCUS research sites. It's actually in Australia, where it's called the CO2 CRC site, and it's sort of the prime project funded by the Australian government. And we've been involved in the very early phases of this project, working closely with Curtin University, and some of the U.S. national labs have been involved in that too. And we're involved in a lot of other research projects over the years here in the U.S., but I think this is the most comprehensive one to give a picture of what you can do for time-lapse VSP. So this project is in rural Australia. It's onshore, and the first fiber optic cable went in 2014, and then gradually it turned into equipping 5 wells with our Carina sensing system, which is sort of our flagship distributed acoustic sensing system that gets the very best performance possible. So a lot of cable in the ground. And then here, looking at rather than using vibe trucks, the goal was to minimize having to bring vibe trucks to site, be able to run true VSP imaging just from a button and run it all autonomously. So what was developed and originally from some research out of Lawrence Berkeley National Lab, now it's a commercial product, are the surface orbital vibes. And so there's two different sizes here, basically to do different bandwidths, different swept frequencies, to where, yeah, you can just run a sweep and the advantage of you don't have any variability in source locations through time. Everything's truly the same, and then you can just run these and sweep for really long periods. So you can really, for a small energy source, you can get the best signal to noise ratio possible, because you're not trying to move between sources. So here's there's 5 wells that were installed, I think, on this map. I think there's 4 of them. No, actually, they're here. And so in black, they're deviated, these wells, and then you can see the SOVs are labeled for SOV sources. So there are 9 sources installed, and then the idea of being able to create these 2D images with the SOV crossline images to get a pseudo 3D view when you combine them of where the plane is migrating. So here's some photos of what the installation of this project looked like. Very similar to what I showed before. Cable protectors going across the couplings, coming out the casing hanger, and wellhead, and then everything spliced. So splicing different wells together, sort of a daisy chain fashion here. So here's a schematic of what that looks like. So yeah, it's really, it's something that really does reduce costs quite a bit, being able to do this and provides a lot of flexibility. And then one question you can see on this well, we get a lot is, okay, what do we, if we're going to perforate the casing, how do we not perforate to the cable? And we can do, you can locate the cable, and so do oriented perforations. There's a few different ways to do that orientation. We make a tool that actually you run it in when you're installing the cable, and it has an accelerometers in it, and it actually emits a frequency tone that communicates what the location is, and then we can actually just listen to that with our distributed acoustic sensor to then do this full cable mapping to the guide perforations. So I think the first questions were, early on in this project, where it was, this new fiber stuff, like how good is the data? Can we actually use this for seismic survey? And so if you look at the top left here, so this is all data from VSP data with a 5-truck source. And so on the left, a geophone array, our IDAS V2, which is using standard telecommunications grade type fiber, and then the Carina IDAS V3 or Carina system is using a specialty fiber developed by Silixa that's fully optimized for acoustic or seismic measurements. And at first glance, you're like, okay, they all look kind of similar, right? So any of them should work. But really it comes down to some of the details. So on the left side, so this geophone array, to create that image, this had to be moved many times and repeat the source many times. So a 12-hour acquisition versus 4 minutes with the distributed sensing system. So really practically, it's a huge cost savings and efficiency savings from the acoustic sensor. And then it's hard to tell on the left side, but we go to smaller sources here on the right. So this is data from SFE sources where you can see on the right in the Carina system, you can start to pick out like the noise field in the background, and you can see how the signal to noise is much better. It's actually a factor of 100 better with the Carina system. So, which really starts to enable more efficient surveys. You can really push the offsets to as far as the great as it could be to get the best coverage possible from a VSP. And then these time-lapse surveys, fundamentally at the heart, you're looking for relatively small changes. So the best data you can get is important. Yeah, so the Carina system. So here, this is the plot of really its noise floor, and you can think of this as like for those non-geophysicists, it's like the background static that's just inherent in the system. So you're trying to get signals that are strong enough to be above that static. So it's really that the noise floor plotted here is a function of signal frequency. And so this is really optimizing in frequencies and what would be typical for these seismic surveys. And so on the top in blue would be our traditional IDAS system. And then you've got plotted here in red and orange what would be noise floor curves for some more traditional high-end seismometer or geophones, or traditional point sensors. And then in the light blue here is the noise floor from our Carina system. So you can see we're really not just matching, we can exceed some of the better sensors on the market. And so here, in practice, here just a different plot of scaling. So you can see, going from our IDAS to a Carina system, you instantly have a boost. It's a huge boost in the noise floor, which is transformed for monitoring. And then if you compare versus the geophones here too, and any geophysicists that were used to looking at this sort of data, it's just like the fidelity, the high frequency content here. It really, you can create better quality images. Data. So practical example here, just to get the same SNR, and in this case, 38 sweeps versus a single sweep. So, which I think there's a lot of advantages, but one is just it's practically just the cost and time spent doing these surveys. So now if we look at some of this data at the time, so here's just base level processing, really to look at the baseline image and then doing differencing and 1 day prior to injection starting, and then really just during the injection. And this work here is all done by collaborators at Curtin University. And I think what impresses me the most when I look at this is the small volumes of CO2 going in. This is a research site. This is very small compared to what we're talking about on the commercial And only 580 tons a week after injection, you start to get the reflector developing from the change in acoustic impedance. So, which is really encouraging as we scale up to some of these large sites. So now if we look at the data post migration and looking at the images, you can see the reflector starting to develop through time. And this is the same data set, just increments on the right hand side. So very, very encouraging, I think, to how this is going to scale up. And then here's looking at some of these 2D sections from the 9 SOE sources to get sort of a pseudo 3D view of how the plumes develop. So now I'll have a few slides talking about an upcoming EGS project that we're working on that some of you might be familiar with, because I know there's broad interest in energy here in the room. So geothermal, really, I mean, there's on the right here is the ways we can break down geothermal energy, and power production right now is it's done through hydrothermal plants. So it's really areas you can go pump out. You can pump out a lot of hot water to flash the steam or use a working fluid that you can flash the steam. But the challenge is there's only so many places in the world where you can go pump out a lot of hot water. We're pretty much tapped out there. There's especially in the US. There's not much we can do there. So there's direct use is growing and heat pumps obviously for heating and cooling buildings. But if we're going to expand the use of geothermal for power production, it's really coming up with alternative ways to extract that heat. And so EGS, enhanced geothermal systems, is really the prime approach for doing this. And so here there's a report from DOE Geovision report from 2019. Really shows that if looking at the growth potential for geothermal, that really, it has to be driven by EGS, which is unproven. There's not an EGS power plant running in the world right now. So it's really, and there's a reason, it's a really big technical challenge. If it was easy to do, it would have been done already, because you're dealing at temperatures that are in the well over 200 C range. So 260 to 300 C is often seen as ideal. And there's a ton of interest in this area right now. But really, we're involved now in the Forge project, which is the US DOE's prime effort for trying to tackle this and to help figure out what tools are needed, what survives downhole, what doesn't, and how do we actually engineer this fractured network so we can run a power plant off of it. So we've been involved for the last few years with some different installations and surveys, but we're really just gearing up this year for this new research project where the goal is to use a variety of techniques to actually characterize the fractured network, both using indirect techniques like microseismic monitoring when we're doing the simulations for creating these microseismic clouds, and then doing time-lapse seismic imaging for looking at velocity anomalies from the simulations. But then at the end of the day, it's really what's the ability to move fluid through these fractures and how much heat does that gain? And it's one of the big challenges. You want the ideal surface area ratio created where you don't want just a few big fractures so you can pump a lot of water through, but it doesn't heat up enough. So yeah, so it's a fairly big challenge. So really over the coming years, we're in the design phase right now and really working on putting together this overall monitoring system using distributed sensing to use these different techniques. And it's a project led by Bryce University that we're participant in. So yeah, we're quite excited, I guess, about this project and what we'll learn that relates to other industries as well. And here there aren't a lot of other techniques that you can use because of the tight temperatures here. So most sensors fail, and we're fiber optics has that advantage of being able to handle 300 C. And then I think this is my last slide. We just finished this primer Whitepaper, working with P4 and ERC, and I think ERC, I think that we signed off on the final version are close, that it's being reviewed. So the access to where it's going to be hosted, and it really will go into a lot more detail than I talked about using distributed fiber optic sensing for CCUS monitoring. And I think it'll be hosted by ERC. Yeah, so that's pending. So I tried to leave a lot of time for questions and discussion because it's not, I don't want you to have to listen to me talk forever. So go ahead.
Sure. For EGS facilities, are those going to be like primary use or are they going to be secondary use? Or do you know, in other words, like, is there going to be some other industrial site there? And it's like, oh, hey, well, we can just add this on and like maybe there'll be a small power plant there anyway. Or is this something where it'll be like, no, this is a designated EGS site and not anything else?
Yeah, well, I think either. I mean,
Okay.
This research project is, Forge is really to understand the techniques, that then you deploy at either type of site and just whether it can be done. Because, I mean, we do hydraulic stimulations, fracturing all the time in oil and gas. Why can't we just translate that and this works? But the difference is, granted, we don't have bedding planes that we can, planes of weakness that are fairly well defined that we can stimulate. Here it's granites and you're following the maximum stress field, and it's a lot harder to control these stimulations, and so it's no small task. So really, it's a technical challenge of just doing it in a way we can control and understand. That has to be solved first.
I have a question with respect to like long-term risk for CCUS. So of course your monitoring system needs to last 30, 40, 50 years. And if you've got, that, it's great. What happens if that's all you're relying on and your cable fails for some reason? Do you guys offer like a solution to that somehow? Or?
Yeah, so I guess I'll repeat for folks can't hear online. The question is about long-term longevity of the monitoring systems, and you have a cable failure and how you handle that. Well, the first step is, I mean, there's a huge variability in cable constructions, and obviously there's things you can do that are pretty cheap versus more expensive, and relates to everything from the glass and the fiber. There's ways to mitigate from having any long-term degradation of that glass, but it's a little bit more expensive to do that. And then different levels of hermetic seals in the cable, and then the metallurgies that are used. And of course, the best ones are more expensive. So I guess that's the first approach, is considering in these applications, these are, these like last decades. So, spending 40% more or whatever on the cable is probably well worth it. And that's something I think we as an industry have to do a better job of educating, because when things just go out to bid and it's not specified these things, of course, you're going to get the cheapest stuff going on the ground. And our worry is then, yes, things fail 5 years or 10 years down the line because it wasn't spec'd, and then gives our industry a bad name, because of that. So that's something we're navigating right now, and I think we need to do a little bit better job of having the standard specs. When we work on a project, CCUS, we're kind of exclusively quoting what we think is the best we can do. But then the next question is, maybe the best you can do isn't good enough. How is it still going to fail? And those are real concerns. But I don't think they're so much different than a lot of the other monitoring techniques that you use. So you can, maybe we have cable installed on the outside of casing that ends up failing at some point. But we could run a cable in the well if needed. You could then back up and run it on the injection tubing later on an injector or a monitoring well, do a intervention style deployment and leave the cable there. So there are ways to work around that, I think, if need be.
And then are you getting the same quality of data that you get if you were like running down the tubing? Because of course, outside the casing and stuff, it's a whole different part.
Yeah. So we for seismic surveying, we actually work. It's quite successful using active surveys with cable run on tubing. I think it really comes down to we're trying to do pressure monitoring and things where you need that coupling, and then your detection thresholds for microseismic events would be a concern as well. So there are concerns there with the sensitivity.
Questions for Thomas? We've got time. Who has a question?
Can you speak to your Antarctica projects at all, or just seismic surveys, or?
Yeah. So Antarctica, we were working on a project. Our first installation there. It's a major U.S. UK joint research project for monitoring the Thwaites glacier, which it's been termed by the news as the doomsday glacier. Anything that can have a dramatic impact, because it's the rest of the size of the United Kingdom, and if it melts, like this one glacier would cause 1 to 2 feet of sea level rise itself. And so what we provided primarily a temperature-based monitoring solution to start for thermal drilling through the ice sheet, and then there's the ice, and then you've got the ocean underneath, and so the cable goes through and then hangs in the water column underneath Antarctica. So there's 3 sites that are instrumented, and then with a primary goal of actually monitoring the basal melt rates on the glacier, because you can monitor the top much easier than the base. So that's the primary goal. And then actually this last winter we conducted a VSB survey using the same cables to actually look at some more properties of that data that's being analyzed. Looks pretty exciting from what we've seen so far, because VSPs through Antarctica don't really exist. So it's pretty novel data set.
I got another question. if you don't mind. So a lot of the presentation you had there was on deep CCUS monitoring. What about, shallow groundwater systems, which are just as necessary? You guys have solutions for that as well?
Yeah, well, we work a lot on shallow systems and other industries. I mean, I guess it comes down to the questions like you could do microseismic monitoring in a shallow system, but your detection thresholds will be lower. I think a lot of the monitoring ends up being geared towards chemical sampling and things in those shallow wells. We work in shallow wells quite a bit, like for flow monitoring, for example. We're actually monitoring discrete flow through an aquifer. So it's really easy to put cables in, and I think I probably haven't thought enough about what applications in some of the shallow wells would be applicable to CCUS. So yeah, I'd be happy to chat with you and see what I have, what we might have missed, there might be some.
Along those lines, do you know if this is used in the monitoring as well as in the in-situ recovery? Rating operation?
I don't think we've worked on any projects in that area.
It seems like it's you're talking about.
Yeah, but it's not an area that we've been involved in or pursued. One of our challenges we're growing pretty rapidly is where we put our efforts into different sectors. Luckily, a lot of the techniques are just common between all of these sectors.
And one of the questions comes from somebody that doesn't know much about fiber optics. On one of the graphs, you showed the various wavelengths you look at. And you had red and purple. So does that indicate that it's infrared and ultraviolet, or just physical?
It's all relative to the different wavelengths. That's a good question. Let me go back to it.
Yeah, it was one of your slides.
Yeah. So we're really, I mean, everything's sort of in this. It's non-visible wavelengths, all in the infrared spectra, but you're really the colors are, you're right. It's going towards the blue or red spectra. So there are they're that direction as far as if it was visible. But yeah, it's all not visible wavelengths here. And there's reasons for that. I mean, the sort of optimized for what you can measure really long distances in fiber with very low optical attenuations. So it's something. It's actually in telecom. You're just trying to get pulses of light from one point to another, and so you don't want any signal attenuation is really bad because you're just trying to get those bits. For us, that attenuation, a lot of that is the light that's naturally being reflected back. So that's what distributed sensing is built on, is that natural reflected signal that we use. Yeah, and I think I talk more in detail about this too. So in this red, so this is really like a log scale. So it's orders of magnitude more light in some areas than another. So it's a reason for acoustic sensing. We can sample at like 100 kilohertz and get really good, meaningful data at those high sample rates. But for temperature sensing, we would measure as fast as maybe every 1 second, even though actually at a raw level, we're sampling at these very high rates. But basically, because the data we're getting, the amplitude of light is much lower, we have to average or integrate for longer. So we're actually measuring, close to 50 kilohertz for one of our temperature sensors, but we're taking those 50,000 measurements to then output one profile. So all these, I mean, it's kind of blows my mind when I think about this stuff. So you're raw sampling the backscattered signal for acoustic sensing or to translate to 25 centimeters in space. So where it's all time based, that's 400 million measurements per second, like raw, that's happening to get to that level of
for our students. So your job seems pretty interesting and awesome. Basically, you're and different projects all over the world. How much travel and involvement do you have?
Yeah, that's a really good question. So for students, how much travel is involved? And it really depends on the position. So one of the areas that we've been hiring the most recently are field engineers, with people that actually go out and do this work, do the installations, collect the data sets. And now it's like, it's so much more than that. You see some of these integrated systems and like, it's a lot of work and training to get up to speed to be able to sort of do all of this. And it's a lot of travel in general. I mean, those positions can be 40 to 50% travel. And it varies throughout the year, but it's mostly pretty exciting travel, I think. And yeah, I'll have to send out a notice next time we're filling positions, because it's something that we want people that enjoy travel, and that this is exciting. I think that many students here might be interested.
Relative to what humans are able to perceive, like what kind of range of like sound frequencies are you able to pick up? Is this like supersonic or subsonic, or is this mostly things that you could, like, if you could put your ear down there, you would go, okay, there's a problem.
Yeah, so much more broadband than the human ear. So at the lowest end of the spectrum, we can bandwidth, like, we set up an experiment where we measured a period. So one waveform, high low, 12 hours. And that's because that's earth tides. So actually looking at earth tide signals. So that's sort of the extreme low end. And then on the, so it's really the translation from like strain sensing is like, it's called a true DC, where we're measuring static changes. So we can measure ultimately from true DC to these low frequency ranges to sampling at, so 200 kilohertz would be sort of the fastest we could sample. So it's 100, so Nyquist, that would be 100 kilohertz frequencies that are resolvable. I'm trying to remember what the human ear goes up to, but it's much lower than this.
Yeah, 20 sounds right.
Yeah. And there, I mean, and those frequencies are very readily attenuated in the subsurface, but we use those high frequency measurements in other areas that we work. I guess there's a lot of other acoustic applications outside seismic where you're interested in high frequencies. And then another advantage is when you're sampling, we'll sample really fast at high frequencies to, it governs the dynamic range of the system. You can sort of think of it as each sample, you can only measure so much stress with the glass before then you might saturate. So if you sample really fast and you're dealing with really big signals, there's another advantage there. And that's something besides just the frequency range. So we can, I had those noise floor plots earlier where it's showing we can measure really low signals at or better than point sensors, but where we actually really exceed is on the high end without clipping. So we can measure all the way up to where the fiber would physically break. So which is around, I think, 3 to 5% strain. So it's just it's a really big advantage besides this distributed nature or these other parameters.
And can you, for us who aren't like fiber experts, what are the advantages of getting, like, so you showed like frequency domain for a bunch of, or like different kinds of sensors and kinds of cables. What are the practical advantages of having that higher resolution? Like, what can I do with that, with the fancy cabling itself, rather than like the byproduct that you showed or whatever? Like, what insights can I gain from that?
Yeah. Well, one is it aids right off the bat with just interpretation, because you're going from a handful of waveforms to actually just being able to instantly visualize the whole wave field.
So less uncertainty.
So less uncertainty. For sure, but then you can leverage that in a lot of other ways. Like you can working with a little bit higher frequencies, for example, and dense receiver spacing. We can improve like you can think of the spatial resolution, the area that you actually image, and so that's an advantage. And when what sort of governs think of it almost as the pixel density of the area they're trying to image it's the ray paths, like from the source receiver pairs. So when you have tons and tons of receivers, then you instantly, for a single source, you have so many more ray paths right off the bat. And because those rays, where the waves are propagating, that's what we're actually the volume we're interrogating of the subsurface. So you're really improving that density by substantially. And then for things like microseismic, there's all kinds of advanced like if you have a microseismic, like a wave hitting, you can actually correct for like the move out in the signal, and you can stack all those channels together to do an even further boost in signal to noise for trying to detect smaller events.
Yeah.
Yeah, it opens up all kinds of interesting things that you can do. And then for like injection profiling, yeah, like that sensitivity is quite important, that sampling spacing for actually allocating flow.
Sorry to interrupt the discussion, but I'm gonna go ahead and close the session. Thank you, everybody, for coming. Thomas, you'll be here the rest of the afternoon. So if there's more questions or you want to pick his brain, feel free to come up and chat with him. So please join me in not congratulating. Thank you. Congratulations.